The prediction of earthquake. Earthquakes occur when energy stored within the earth, usually in the form of strain in rocks, suddenly releases. This energy is transmitted to the surface of the earth by earthquake waves. The study of earthquakes and the waves they create is called seismology. Earthquakes vary from small, imperceptible shaking to large shocks felt over thousands of kilometers. They can deform the ground, make buildings and other structures collapse, and create tsunamis. The destruction an earthquake causes depends on its magnitude and duration, or the amount of shaking that occurs. Most earthquakes are caused by the sudden slip along geological faults. The faults slip because of movement of the Earth's tectonic plates, which flow very slowly on top of a fluid rocky layer. As the plates collide with each other or slide past each other, pressure builds up within the Earth's rocky crust. When pressure within the crust increases slowly over hundreds of years and finally exceeds the strength of the rocks, it will suddenly be released, causing earthquakes to happen. The slip begins at the focus and travels in irregular steps along the plane of the fault, radiating waves out along the rupture surface. The slip also changes the local strain out into the surrounding rock and leads to aftershocks, which are produced by further slips of the main fault or adjacent faults in the strained region. These sudden stops and starts of the moving rupture give rise to the continued vibrations that propagate as seismic waves. After the earthquake, strain begins to build again until it is greater than the forces holding the rocks together. Then the fault snaps again and causes another earthquake. Such effect is like the sudden breaking and snapping back of a stretched elastic band, and therefore is called elastic rebound theory. Seismologists try to predict how likely it is that an earthquake will occur with a specific time, place, and size. Earthquake prediction also includes calculating how a strong ground motion will affect a certain area, if an earthquake does occur. Yet, even with precise instrumental measurements of past earthquakes, conclusions about future tremors always involve uncertainty. This means that any useful earthquake prediction must estimate the likelihood of the earthquake occurring in a particular area in a specific time interval compared with its occurrence as a chance event. Seismologists have developed field methods to date the year in which past earthquakes occurred. In addition to information from recorded earthquakes, scientists look into geological history for information about earthquakes that occurred before people had instruments to measure them. The growing catalog of both recorded and unrecorded earthquakes can help scientists estimate when and where strong seismic motions may occur. They map past earthquakes to help determine expected rates of repetition. The elastic rebound theory also gives a generalized way of predicting earthquakes because it states that a large earthquake cannot occur until the strain along a fault exceeds the strength holding the rock masses together. Seismologists can measure movement along major faults using global positioning satellites, GPS, to track the relative movement of the rocky crust of a few centimeters each year along faults. With the help of such information, they can calculate an estimated time when the strain along the fault will be great enough to cause an earthquake. As an example, after the 1906 San Francisco earthquake, the measurements showed that in the 50 years prior to 1906, the San Andreas Fault accumulated about 3.2 meters, 10 feet, of displacement or movement at points across the fault. The maximum 1906 fault slip was 6.5 meters, 21 feet. So, it was suggested that 50 years times 6.5 meters, 3.2 meters, 21 feet, or 10 feet, about 100 years, would elapse before sufficient energy would again accumulate to produce a comparable earthquake. Scientists have measured other changes along active faults to try and predict future activity. These measurements have included changes in the ability of rocks to conduct electricity, changes in groundwater levels, and changes in the variations of the speeds at which seismic waves pass through the region of interest. None of these methods, however, have been successful in predicting earthquakes to date.